So thank you everyone for joining us today. So today we will talk about Rust. So some magic with Rust on CPU and GPU about computing with Hadrien. So before I introduce Hadrien again, I will briefly talk about Karim and Marie. So they are working in Terratech and they help us to organize the school. And they also part with the Terratech from EuroCC, and EuroCC, you know, is the teaching part of all the Euro HPC project. And their goal is to organize and to speak about a lot of formation, a lot of teaching, webinars, interviews, and school about high-performance computing, high-throughput computing, AI, quantum computing, all this kind of computing stuff. And last year, they helped us to make the Grasland School 2024. So in Annecy, but also in 12 satellite sites over 4 countries on 2 weeks. So it's a really long school, 2-week school. And we have 9 teachers, part of the dream team. You can recognize some of them here. You have Joël, you have Hadrien, you have Sébastien here, Vincent, Alice. I'm here, Karim is here. Marie is here, so normally you should spot quite everyone. David is normally hidden somewhere because David hates photographs. Yeah. And so the idea of this school is to give you an overview of all the technologies that you can use to do some computing with high-performance computing on CPU and on GPU. So the first week is on CPU, and the second week is on GPU. And we will have a lot of hands-on on the school also, and a series of webinars. So this year we have 17 webinars on the Grasland School because of the calendar. Normally it's 20, but this year we have some day out the Thursday. So it's a pity, but it's life. And so before continuing, I will start the trailer to show you an overview of all the school.
Do you sometimes feel limited by your resources or unsure how to maximize the potential of your HPC resources? Imagine a place where collaboration, creativity, and learning converge with high-performance computing. Welcome to Grasland School 2025, Europe's leading summer school for HPC. Taking place from June 23rd to July 4th. Over 2 weeks, students, academics, and industry professionals from across Europe will explore the frontiers of programming while building a vibrant community. Together, we'll discuss programming and optimization on heterogeneous architectures, highlighting their respective characteristics and limitations. You'll have a unique opportunity to explore generic optimization methods, as well as the latest technologies and languages for achieving optimal performance. The school is free and open to everyone, and you can participate in person in Annecy, France, with the teachers, at one of our satellite sites in Europe, or online via our live streaming. You can choose from an intensive program or a la carte courses to develop your skills at your own pace. With the first week dedicated on CPU and the second on GPU architectures, you will study computational accuracy, vectorization, parallelization, compilation, memory profiling, unit testing, and the various programming languages C++, Fortran, Rust, Python, and Julia. In addition, we will study the MPI, OpenSHMEM, OpenMP, TBB, EVE, Kiwaku, Sycl, Thirst, CUDA, OpenACC, Vulkan, NumPy, Number, QPy, CU-numeric, JAX libraries, and Legit, as well as computation with PyTorch and TensorFlow, and the G++, Clang++, NVC++, NV Fortran, G Fortran, and DPC++ compilers. Throughout the course, you'll discover and use profiling tools such as Valgrind, Perf, Macau, Nsight, Malt, and NumaProf. Each session leads to a practical challenge, the simulation of Gray-Scott's diffusion reaction, which tries to describe how a chemical reaction evolves over time. Simple to understand, but complex enough to push the limits of optimization. Thanks to our specially designed Docker containers, you'll have access to a complete working environment to follow courses and exercises on your laptop or supercalculator. Throughout the program, you'll be guided by a dozen expert instructors, leaders in the field of programming and HPC. You'll have the opportunity to ask questions and chat with them live on Discord, so you can tailor your learning to your needs. Join our growing community of over 500 users to find answers, exchange ideas, take on challenges together, and build bonds that will last well beyond the program. You can also join the Grey Scott School European network of satellite sites, not only to attend the courses, but why not become a satellite site yourself and host the school in your location? You just need to provide a room, a contact person, and access to computing resources. We'll provide courses, tools, and Docker containers for a seamless learning experience. Grey Scott School is free and open to all. It's your chance to master advanced programming and optimization, engage with a growing European HPC network, and push the boundaries of technology and training. You can kickstart your journey now by joining Grey Scott Thursdays, a free webinar series previewing the school's courses. Don't miss out. Register today to attend, whether in person in Annecy, France, or at one of our satellite sites in Europe, or online via our live streaming. Grey Scott School 2025, where HPC meets your potential.
If you have some question regarding the school, you can ask them in the Q&A section after the session. And so back to Hadrien. So Hadrien is a research engineer at IGC Lab, and he's mainly involved in SCTS programs, so common tracking software used in HCB, in Atlas, in big experiments like this. He's really fond of Rust, so we'll talk about Rust also today, particularly of how to compute on CPU and on GPU. We'll see that it's really powerful, really powerful language. And that being said, I will give the floor to Hadrien, and I wish you a happy webinar.
Welcome to this webinar, where we will discuss, we already did one webinar on Rust previously, which was about reasons why you might want to consider Rust for your next numerical computing project. More of a design discussion, how Rust differs from C++, why I compare these two languages, and so on. Today will be a more practical angle on what high-performance numerical computation actually looks like in Rust. But because not all of you may be familiar with Rust, I will start with a numerical hello world, which is a loop. So let's look at this in loop. You say for e from 0 to 5. We'll see what that means in a minute. And we print I. We can run the code. And we see that it prints 0, 1, 2, 3, 4. So what can we learn from this? Like Python, Rust defaults to half open ranges that are closed on the left-hand side and open on the right-hand side. This is, there are reasons for this that go back to the ages of computing, but basically they have better mathematical properties overall. This is not to say that Rust is married to this kind of ranges. You can also have ranges that are closed on both sides, as in Pascal and Fortran, if you like, and you can have unbounded range and other kind of ranges. Because ranges are not only meant for iteration, you can also use them, for example, for indexing arrays. And this means that you can have any combination of closed open bounds, and the bounds do not need to be integer numbers. Now, if we look at this loop, actually what happens under the hood is that the compiler will translate into slightly more complicated code. So first of all, the compiler will take the object that we put on the right-hand side of in, and it will turn it into an iterator using the into iterator trait. It will then proceed to ask this iterator for its next item. And as long as it returns an item, then it will do what we ask, so printing. This translation means that for loops are not limited to integer ranges. They can work with any kind of iterable object. And in particular, this lets us do fancy things with iterators, as we are going to see. Rust iterators have what's called adapter methods. These methods basically consume an iterator and turn it into a different kind of iterator. So here I have an example where I start from the half open range that starts at 2 and goes indefinitely. I turn this range into an iterator. I ask it to step by 3 steps, which means that I only take one element, skip the next 2, take one element, skip the next 2. Then I say, actually, I don't want the first element, so I will skip it too. And I only want 4 elements overall. And then once I'm done, I want to, after finishing this iterator, start going over a different iterator. And this I can do with the chain adapter. And finally, I may want to have some number that identifies each value starting from 0 and growing. And this I can get with the enumerate adapter. And by doing this, we will get this sort of pattern. So first, the inner iterator emits the value 2. We skip this one. Then it ignores the next 2 values. So 3 and 4 are ignored. Then it emits 5. This one we accept, so we emit it. Then it continues going every 3 elements for 4 steps. So we can get 5, 8, 11, 14. And once we are done with this initial iteration scheme, then we switch to another one. So we do 1, 2, 3. So as you can see, by chaining these simple building blocks, we can build arbitrarily complex iteration patterns. And this is where you may be worried about performance, thinking, oh no, do I need to, call some kind of virtual method every time we call iterator.next? Actually, that's not the case, because iteration is lazy in Rust. An iterator does not start working. You call the next method, and this allows the compiler to apply many optimizations. Ranges are not the only kind of iterable object that can be limiting, so we can iterate over collections. At this initial stage of the presentation, I will only discuss 2 collections. One is a stack allocated array, which look like this. So a square bracket, a bunch of value, and another closing bracket. And then we can iterate over them. So this will print the first element, the second element, and the third element of the array. And then we have heap allocated array. And here I show a different initialization syntax that you can also use with stack allocated array, where instead of specifying values one by one, you say, I want each element of the array to have the same value, and I want the array to have this number of elements. So in this case, I want it to contain the value of 2 repeated 3 times. And I say this is a heap allocated array by using the vec macro here. And I can iterate over them, print the content, and it goes as you would expect. These are not the only collections available. We have hash maps, we have B-trees, a lot of powerful collections, a bit more than in C++, but it's mostly comparable. However, before you can make good use of collections in Rust, there is one important concept, rather unique in this language, that you need to understand, which is ownership. So let's move to that. The basic new thing in Rust with respect to most other language that you will need to get used to in order to be productive in this language is that anytime you use a value, by default, you will move it. If you're familiar with C++11, this is as if you used std move in C++11. So the idea of moving is you take the value to a different place, and the original value cannot be used anymore. However, this is a bit simpler in Rust than in C++11. First of all, in Rust, all types can be moved. You cannot delete the move constructor. It's always to move something. And second, moving is always equivalent to doing a bitwise memory copy of the content of the object, followed by making the original object inaccessible. And this is done that way because, first of all, it means that programmers do not need to implement move semantics by hand. It's almost always a good implementation for what people want with move semantics. And if it's predictable, it's easier for the compiler to optimize. And there is a third new thing, which is related to Rust's safety goal, which is that in Rust, the compiler will check for you that you will not use the original value after moving it. So if we take this code, for example, here we declare a heap allocated array, which is something that cannot be copied. We'll see what that means later on. Then we iterate of it, and this will consume the value. So we will, but in the process of printing, we will destroy this heap allocated array. And then if we try to reuse it, the compiler will tell us that no, we can't, because we are trying to borrow something. We can see what that means later on after moving it, and that's not legal. Now, I mentioned earlier that in Rust, moving is defined as an equivalent to memcopy in C. And there are some kind of objects for which memcopy actually makes an independent copy of the object. So this is not the case for heap allocated array, because we cannot just copy a heap allocation by copying the pointer to this heap allocation. The reason is that if we liberate the original allocation, then the pointer, the copy that we make, is invalid. But if we take stack allocated array, it's fine. We can just copy it on another place on the stack. Rust then allows us to reuse the original value. So basically, we have a way to say that for a type, memcopy makes an independent copy, and then we switch from move semantics to p semantics, which will be more familiar to people from C++. So here, this stack allocated array, where memcopy effectively creates an independent copy. We use it. This makes copy of the elements, and then we can continue using it again. That's fine. For objects where copies are equivalent to memcopy but involve a more complicated operation, we have an explicit operation called clone. The reason we have that is that this avoids accidental performance problems linked to making excessive copies of objects, as we often observe in C++. That being said, copies are not always the right move, if you may tolerate this pun. The problem with copies is that if the compiler does not manage to optimize them out, then copying objects from one place to memory, in memory to another many times can become costly. This is why in code that is performance critical, you should really, most of the time, prefer in-place access, using something called borrowing, which is similar but not identical to references and pointers in C++. We have two flavors of borrowing, one which is called shared borrows, which in most cases is about read-only access. So here, I make an array with a bunch of numbers. I do a shared borrow of it, and I iterate of that borrow, so I get references to each element, and I can do read-only operations on these references, like printing them out. I can also have write borrows using this variant of the borrowing sign. Here I just tap an ampersand, here I tap &mute to indicate mutability. And then I'm allowed to do writes and then replace everything by 4.2, because that's almost the answer to everything. And in the end, I still have access to the original value and I can print it. This shows, again, here we can print the original array contents, and we can modify it and print it at the end and see that it's indeed been modified. There is a price to pay for Rust safety guarantees, which is that we have restriction on this borrowing operation. Basically, they have reader, writer, lock semantics. At any point in time in your program, you can have either one writable borrow to a value, also called an exclusive borrow for this reason, or you can have n shared borrows. Shared borrows are most of the time they only provide read-only access. However, there is something called internal mutability, which allows you to modify value to which you have a shared borrow, which is necessary in order to allow things like mutexes for synchronizing threads, for example. Two other restrictions that will make sense to the experienced C and C++ programmer is that borrows cannot escape the scope of their parent variable, because if the parent variable goes away, then what does your pointer point to. Same way, if you modify the parent variable, you invalidate any borrow you have made from it. And this is to prevent a very common kind of bug in C++, Java, C#, Python, which is called iterator invalidation. I know that this may be a bit fast. The first time you see this concept, they can be a bit confusing. We'll get back to them as many times as required during the course. But for now, let's get back to our iterators and see how we can put these concepts in practice. We have more iterator adapters than I have discussed before. We have, in particular, two ones, which are map and collect. The map iterator adapter works by taking each element, the original iterator, passing it through a function, getting the result, and producing the iterator of results. So here I have an array of values which are all equal to 4.2. I turn this array into an iterator. I pass it to a function that elevates each element of the input operator to the power of 2, so it squares it. And then I use another iterator adapter called collect, which allows me to build a collection from an iterator. And it can be any kind of collection. You can build hash maps from iterators. You can build a linked list if you really want, hash sets, anything. And in this way, I can easily turn one collection into another. So here I have an array of 4.2 and stack allocated array of 4.2, and I turn it into a heap allocated array of 4.2 to the square. This may not sound so interesting right away, but if we introduce another iterator there, which is called zip, then we get another power, which is the ability to turn a pair of iterators into an iterator of pairs. And by combining that with the other adapters we've seen previously, we're able to implement the classic Saxp operation from BLAS. So the idea here is we have two arrays, one constant. We turn the first array into an iterator. We zip it with the second array. Here we do not need into iter because this is done implicitly by zip. We call map to turn each pair of elements from the input arrays into the constant times element from the first array plus element from the second array. And from that, we build another array. There is one thing to bear in mind when you do zip, which is that all implementations of zip in programming language need to deal with the problem that the two iterators you're zipping may not have the same length. In Rust, the semantics that were chosen is that it truncates to the length of the shortest of the two input iterators. This is better than in C++ where you get undefined behavior, but it's still something that's a common source of error and should be watched out for. The iteration model that Rust uses is a lot more flexible than the SEL algorithms that we have in C++. It composes to arbitrarily complex operations, as I have alluded to earlier, and this means, for example, we can do triadic operations like FMA very easily. We just, start from our XY pairs and just add a Z to it. And this gives us a tuple of one tuple of XY and Z. And then we can do multiply add for FMA as we like. And we get an array of FMA products, so to speak. And sorry, I have not updated this code, but this should use a debug printout. Anyway, it works. Then we have reduction methods, which are about taking an iterator, turning them into a single element. And the simplest one of them is sum for numbers, which computes the sum of the numbers from the input iterator. So here we have an array of 10 floating point numbers, all equal to 4.2. We iterate over it, we sum it into floating point number again, and we get 442, sorry, because this is 4.2 initially, almost because this is floating point. There is just one problem for our purposes, which is that these methods do not compile into a very clever loop. They compile into a basic loop. In the case of sum, basically you start from the neutral element of the sum, which is 0. You iterate over the elements of the input iterator, and we add each element to the sum. And if you've ever been doing any kind of high-performance floating point work before, you know that this is not optimal. Because if you do that, you force the compiler and the hardware to do the sums one by one, which will result in poor runtime performance. To do better, we can add instruction level parallelism. This is what std_reduce tries to do in C++20. I have written a library that does similar things in Rust called iterator ILP. But there is one particular hardware facility that is somewhat hard to use with instruction level parallelism alone. It may work, it may not, depending on what is the mood of the compiler today. And for vectorization, I advise that you do not play this game and just use explicit SIMD instructions when you. Explicit SIMD right now is a bit clunky, but is getting better relatively soon in Rust. We have an experimental feature in the std_cmd module of the standard library that you can use on likely versions of the compiler. And the idea is this. So you start from your collection of scalars, and you can use the ascmd method to split it into 3 slices. That you can think of this as views into an array, which are unaligned scalars at the beginning, unaligned scalars at the end, and aligned CMD vectors at the middle. Once you have that, you can iterate over the CMD vectors, sum them, and this will use CMD instructions. And in the end, you get a sum of CMD vector, which is a CMD vector, and you will want to reduce that into a single scalar. We still need to take care of these unaligned scalar element at the start and the end, and we can do that by using a usual iterator pipeline. So we iterate over the initial elements, chain or sum of the middle elements, chain the later elements, and we sum all of that using a scalar sum. This will be slower, but it's okay because we are only summing few elements here. There is one last performance issues here, which is that we are not leveraging superscalar parallelism in this part of the loop. By adding some instruction level parallelism, as discussed by Pierre in his previous, you can get the peak hardware performance that you would expect. So that's it for nightly Rust. It's going to be awesome, but it's not quite there today if you're using stable Rust. So what do we do today? We have 2 relatively good approximations of std_cmd available on stable Rust via external libraries. We have Slipstream. So what Slipstream does is it tries to make loops that the compiler will have a higher chance to auto-vectorize. And the way it does this is that it makes you manipulate objects that, like Canada Dry, they smell like CMD vectors, they taste like CMD vectors, but we are relying on the compiler to turn them into actual CMD vectors. Another option, if you only care about the Intel and AMD CPUs, is Safe Arch, which tries to reduce the pain of using processor intrinsics by giving them a better name and some basic object-oriented methods. Here is a little performance comparison of how you can get using various methods. So if you use the just, iterator sum, you are here. That's not great. You are like 10 times slower than the other options, even when you are memory bound for large input arrays. And then we have intrinsic implementations based on Safe Arch, which are done here for SSE, here for AVX, and here for AVX 512. You can see that these are not quite the factors of 2 that you would expect. And the reason for that is that we run out of L1 cache relatively soon. And this means that we are by the bandwidth of the cache before the CPU has gotten the chance to get to optimal loop processing speed. As you can see here, here it's processing elements, but the rate that processes elements per second is increasing because basically the longer the loop, the more the CPU can be efficient. You can see that when we use std_cmd, we are right next to the hardware intrinsics, as we should be. There's a tiny difference, but it doesn't matter for our purpose. It's a small difference in code generation, I believe. Slipstream does not quite manage to get, it's somewhere in between SSE and AVX intrinsics in terms of performance. So it's decent, but not great. You will see that it's suboptimal when you're doing cache local data, but for data that requires access to the L3 cache or main memory, it doesn't matter. Just for context, this is where you would get if you use the pure instruction level parallelism auto-vectorization method. So it's already much better than the naive sum, but it's not quite where you can go with explicit CMD programming. We have discussed SAXP and reductions, so you may think it's time to do dot products, which are basically the combination of the 2 operations in some respect. You would expect that we can just, take our 2 input arrays, iterate over the first array, zip the second array to get an iterator of pairs, take these pairs, multiply the products with each other, and compute a sum, and we would be done. We will get the correct result by doing this, and it's a very elegant programming model. On the other hand, we will again face the performance problems linked to sum because, as I mentioned earlier, the basic implementation of the sum reduction is not at all optimal for floating point data. Another issue with the dot product is that we cannot use the as SIMD trick we used before to turn our unaligned scalar data into aligned SIMD data. The reason for this is that X and Y are two independent scalar allocations which may have distinct alignments. So when we extract the aligned part of each array, we may not extract the same aligned elements. We may be trying to sum the third element of X with the fourth element of Y, for example, and this will not be good. This is why for any kind of more complex vectorized operation, I highly advise that you do not use scalar data like this internally, but instead use a native SIMD data format where your data is already prepared in SIMD vectors. And then you avoid all the issue of processing the unaligned part of the beginning, end of the array separately, and so on. And you can implement operations like dots easily as a bonus using the techniques we saw earlier. There is one optimization that we can play for dot product, which is that on many CPUs, we have fuse multiply adds that are as expensive as multiplies and adds for floating point taken separately. This means that if we take our iterator of pairs, we can replace our map and sum with something called fall, which is a custom reduction where we specify, we start with a certain accumulator value, in this case, the default value, which is 0. And we say, given each new pair of inputs and the previous value of the accumulator, how will we generate the next value of the accumulator? As mentioned earlier, we need to work on this a bit to get good performance. We need to add some instruction level parallelism. But at the end, we will get this. So again, STD SIMD is here. You see that FMA, again, is not quite a factor of 2 over the just multiply and addition pairs. And again, the reason is that our loops are a bit too short to get the CPU to process data as optimal speed. We see that for this operation, actually, just pure instruction level parallelism is not that bad. It gets something relatively reasonable. Here you have it with FMA, here you have it with multiplication, and you can see that when you're not processing work efficiently, the relative differences are larger, which is something to bear in mind when you optimize. And again, we are much better than we would have been if we just, did this with scalar data. Now we have still one big part of our computer that we are not using, which is the fact that we have multiple CPU cores. So it's time to think about parallelization. Using the Rayon library, we can actually do parallelization as easily as we would do scalar iteration. And that's one big reason for using iterators for computations. So here I'm just playing fancy boy by showing that you can, create a pair of an array of things and decompose it into 2 variables. That's unnecessarily fancy. The important part is here. So as you can see, I can take my 2 arrays of inputs, and this time instead of turning it into an iterator, I turn my first array into a parallel iterator. And then it's a lot like what I have in sequential iteration, just a tiny bit different. The fold operation, instead of asking me for one initial value, asks me for a recipe to produce as many initial values as needed. This is necessary because since we are doing now parallel summation, actually dot products, we need to have each CPU work independently. And this means that each CPU will start with its own initial value and then do accumulation on its side. The rest is similar. So we explain how one accumulator value integrates new input and becomes a new accumulator value. And at the end, we get a bunch of accumulators because, again, we have been doing parallel dot products. So each thread produced independent subsets of the dot products, and then we sum this subset to get the final dot products. What's new here compared to other programming languages is that due to the way borrowing works in Rust, we are immediately protected from unprotected concurrent access to data. We cannot introduce data race and define behavior by like trying to write to a value from different threads at the same time, for example. This will not even compile. The compiler will right away say, you cannot do this. And that's a very powerful help, which is why it's much more common to parallelize software in Rust because it's so much easier. If you're curious, under the hood, Rayon works very much like Intel trading building blocks. So first, you take parallelizable tasks, have the ability for each task to cut it into two parts that should represent roughly equal work. It does not have to be exactly equal because we have load balancing. Then before it starts to process a task, what a thread will do is it will cut it in half, put one half aside in a place that other threads can access. And the reason it does that is that if later another thread runs out of work, it can take work away from the processing thread by stealing the other half of the work. This is called work stealing and is an easy way to get load balancing, which means that unlike most parallel programming models, Rayon will work well with irregular algorithms like graph process, for example. However, doing all this is a bit inefficient. So there is a mechanism so that once threads have a sufficient amount of work to do, execution will eventually become sequential and stop doing this splitting and taking back. Now, Rayon was tuned in terms of implementation for tasks that are significantly more complex than dot products. Think stuff like, processing internet connections on a server, processing a bunch of images in an image editor. And this means that its default settings are not quite right for our purpose when you're doing dot products. So here we can see the performance of the naive dot product, the performance of our optimized sequential dot product, fully optimized, and what we get with Rayon for different amounts of threads. What you can see here is that the more threads we use, the worse it gets. Basically, we start much, much worse than even the unoptimized sequential operation. And then we grow, and eventually around 100,000 elements, we start to be faster in parallel than sequential. And ultimately, when we are memory bound, we get to some optimal speed, which is limited by the memory bandwidth available to all CPU cores. This is not great. So the hyperthreading part we can fix. The way I produce this graph is just by using the Rayon numThread environment variable to tune my number of threads, as I do with OpenMP. There is also one API for doing it from your code. But we can do better. And do better is by telling Rayon that actually we do not want it to split work indefinitely. We want it to stop at a certain granularity. It calls the chunk size. And below that, use some sequential algorithm for processing each individual chunk. This will reduce the amount of available potential parallelism and opportunities for load balancing. But in our particular case, there is still more than enough opportunities. So this optimization is very much worthwhile and will give us about 3 times speed up at the region where parallelization is worthwhile. Overall, Rayon is a very nice library for doing parallel programming. It's a great improvement on anything else that came for it, in my opinion, in terms of ergonomics. But it does have a few shortcomings that I am unhappy about. One is that the cost of scheduling a task, so this pushing work away for the consumption of other threads, is relatively high. It's a few microseconds. That may not sound huge, and indeed it's not an issue if you're doing coarse-grained parallelism like batch image processing. But for simple tasks like dot, where the work you take to process each element of your array is very small, 1 microsecond is thousands of CPU cycles, and it's an eternity. Like our CPU can process the full contents of its L1 cache in 100 nanoseconds. This is more than 10 times more. So there is a real opportunity here to optimize the implementation of Rayon so that it makes task scheduling cheaper. And they have a few demonstrators that show that this is possible. We just need to integrate it. Another issue of Rayon is that, like many parallelization libraries, it does not take irregular memory accesses into account. Think things like non-uniform memory access, when you have multiple CPU sockets that each access their own private RAM sticks. Think also non-uniform cache access, as you have on many modern Intel and AMD CPUs, where the L3 cache is actually sharded in multiple blocks. And if a CPU core tries to access the L3 block of another CPU core, it pays a penalty. To correctly take this into account, the work stealing scheduler should penalize work stealing across memory domain, because this will ultimately lead to slower remote memory accesses. Today, Rayon does not do this, so we are forced to do what everyone else does in HPC, which is to spawn one application process per memory domain and synchronize them using distributed techniques like MPI. It works, but it's not happy. Previously experimented with a more optimal way to do this. Unfortunately, ran out of time, but you can study it if you want. But what I want to stress here is that we are hugely benefiting for this sort of R&D from the fact that Rayon is just a normal library. It's not, as in C++, something from the standard library where if you want to contribute, you need to get in touch with the ISO standard people, which costs money. You need to contribute to compiler code base, which use development workflows from the late century. It's much easier, you're just contributing to a library like any other. So I hope that this will allow this sort of improvement to take place ultimately. Anyway, so far we've been doing simple computations. Now it's time to move up the scale and start using more complex primitives. Because we are numerical scientists, we love algebra. And in particular, we love linear algebra. So what options do we have for that in Rust? Like in C++, we have many options. If you've ever been too long in programming, you will take the cynical view that this means that none of the options are great. The main option that I would advise studying is ND array. What it does is it provides you with a basic n-dimensional dynamic array structure similar to NumPy in Python. And then you can it provides iteration algorithms, slicing views, and then you can plug in extra plugins for linear algebra, statistics, random number generation, etc. This would be, in my opinion, the default choice when you do not have a reason to pick something else. It has relatively good ergonomics. It's very flexible. You can do a lot more things with it than with the other libraries if your requirements ever change. And it has decent performance. Still, for a more traditional linear algebra focused library, you have NAlgebra. Its main perk is that it allows you to define the size of matrices and vectors at compile time, which allow them to be stack allocated and allows the generation of optimized inline code, which is better when you need to manipulate lots of small vectors and matrices, as we do in particle physics. As for emerging libraries that I'm not sure if I would advise using them quite yet, but they are extremely interesting. We have FAIR, which is aims to be more performant than what came before it. Basically, any performance that is lower than Intel MKL is considered a bug that should be fixed. And it already produced some promising results that you can consult with this link if you follow the slides in the chat. Unfortunately, it is less mature, it has poor documentation, and it does not yet have purpose for the kind of compile time sizing that I mentioned earlier. It also does not have support for n-dimensional tensors today. Your best choice for this at the moment is ND array. But both of these are envisioned as possible future extensions as the library mature. And finally, we have a lot more options that are focused on the needs of people doing 3D graphics who, do not want to deal with the complex general API for manipulating arbitrary n-by-n matrices, rank n tensors, and so on, and do simpler things. You have GLAM, Euclid, CGMAT. So what does ND array look like? You first bring it into scope using this after adding it to your dependencies with Cargo. And then you have access to a macro called array, which allows you to declare n-dimensional array using syntax that is similar to that for creating normal one-dimensional array, And you also have constructors, as in NumPy, where you can say, I want a bunch of zeros with this shape. One thing that's a bit puzzling when you get started with ND array is that it has two different iteration APIs. It has its own optimized API that calls the producer API. Here you can see it in action. So you say that I want to iterate over rows of my matrices. Then I get rows. Here I get mutable rows that I can modify. Here I get read-only rows that I can modify. And then I can iterate over the output row of the output matrix, zip it with columns of the right-hand side matrix, and compute dot products of the rows of the left-hand side matrix and the columns of the right-hand side matrix. So as you can see, here we are using the optimized iteration API, the producer API, and here we are using the null iteration API, which is also supported. The reason why ND array has these two APIs is that The producer API exposes additional information like, which elements from the iterator are contiguous, what is the memory layout, and this allows it to implement some operations more efficiently. Now, anytime I show matrix product example on a slide, I'm getting nervous, so I want to stress, you should not ever implement your own matrix product if you don't have a very good reason to do so. There are very high quality implementation in there, and this one in particular is terrible. For one thing, the second matrix, which you access column-wise, is accessed very inefficiently using a strided memory access pattern, which will destroy your cache locality. Because of the above, it gets no benefits from vectorization. The cache locality is going to be bad. You are not going to leverage your CPU cache to the fullest extent because we are not using loop blocking as we should. We are not doing parallelism yet, so this is a single CPU core. And this is a pity when you could just, type x dot y and be done with that. And since some people cannot take slides as advice, I just put a graph to show you that this is the naive matrix product I showed above. This is the one you get from a professional BLAS. It may be a bit faster for tiny matrices, but generally, you should almost always use your linear algebra library and not run your own. Let's move on now that we have covered pretty much all CPU topics to GPU. Here, I find that people have many different needs, so I like to define first what is my ideal GPU framework for my own GPU programming experience. Many GPU frameworks sacrifice portability, make it harder to build an application that runs on any hardware but that of a single manufacturer, typically NVIDIA. I don't like that. I think we are repeating the same mistakes that people did in the 60s where they wrote code that only works on VAXes. I don't know if you still have access to a VAX or PDP-11 today. Probably not. That proves my point. So I want portable code that I can easily port to many hardware and operating systems. I want development and runtime environment that are easy to install and easy to keep working over time. So many GPU frameworks are a huge pain to set up on your system and will break on the first kernel operating system update. This should not exist in the 21st century. This needs to go. I want my preferred GPU API to be well supported by the manufacturer, which means I want to have tools. I want to have debuggers, profilers. I want to be able to file support tickets to the manufacturer and get answers. And this will be a problem for API like OpenCL, which some manufacturers like NVIDIA do not consider high priority because they let you port your code to that of other manufacturers. I don't want to depend on manufacturer goodwill. I want to have support because the manufacturer is forced to provide good support. I want to have an easy time writing code from the GPU kernel to the plumbing code on the CPU side that gets the GPU code to execute. I want to have full optimization potential, not only good performance for my first try, but as soon as I start to optimize, I want to have access to all the hardware features, subgroups, textures, tensor cores, and that's a common shortcoming of a portable framework. They often forego this sort of low-level access. I want to have it. I would like to minimize the code duplication that I have between code targeting different GPU manufacturers. It's okay sometimes to have some targeted optimizations somewhere in your kernel that only concern one manufacturer, but I want to have as few of these as possible. I want portable code to run pretty much as efficiently as hand-tuned code whenever possible. And finally, we are using graphics processing units to do computation, and we always forget about this. But this should mean that we should have an easy time visualizing our work. It should be easy to build a real-time visualization with fancy 3D effects, scaling to huge walls of screen if you want. And this is, again, a common shortcoming of GPU computing framework. It is they make it a pain to integrate with things like OpenGL and Vulkan. Finally, there is something which I do not consider to be a goal for a GPU API. Many GPU portability API aim to achieve code sharing between CPUs, GPUs, and FPGAs. In my opinion, this is a mistake. We've been trying it for many years. Many frameworks in this respect have been devised, and anytime people have tried to use them, they always reach the conclusion that as soon as you start to do something more complex than a matrix product with them, your code is horribly complex, the API is horribly complex, the runtime performance is generally horrible on all but one single hardware platform. In my opinion, it's not worth the trouble. You should accept that if you are targeting CPU and GPU, you are going to need CPU kernels and GPU kernels. That's life. There is one GPU programming technique that will give you 90% of what I want, and that's graphical APIs. They are optimal in many respects. They are designed to be portable to many hardware. Their development and runtime environment are omnipresent, easy to install, easy to deploy to production, and very reliable. Because graphics programmers need performance too, they have pretty good support from the manufacturers, tooling, and again, the manufacturer is forced to provide support for the portable API, because in graphics, that's the norm. APIs are meant to implement the latest game from Ubisoft, which pushes your GPU to the limit, so they give us to almost every hardware functionality you want. They have no shame against something like CUDA. That's a common mistake of compute people, to think that you need a dedicated compute API for this. Mostly you won't. They allow you to achieve good code sharing across GPUs, because they have been designed to encourage you to write code that's efficient on many hardware. And because they are designed for graphics, they are perfect for visualization. Still, graphics API is a broad category. There are some nuances between APIs that guide your choice. If you need to target a very old hardware and operating system, your best choice is OpenGL. For any kind of modern GPU, however, you will want to avoid it because it has many problems that come from its old age. Like, it's OpenGL is based on the idea that putting all the state of the graphics API into global variables was a good idea. We since learned this is not the case. We want to have explicit state management. So what about Vulkan? Well, on Linux, Vulkan support is excellent. If you have any kind of graphics running on your machine, basically you can expect Vulkan to work with zero extra effort. And development tools are trivial to install as well. They are packaged in all common distribution. On Windows, it's a bit trickier. Because Microsoft develops a competing proprietary graphics API, graphics driver that you get when you initially install Windows may not provide good support, Vulkan support. That's fine. If you get this issue, you just go to the manufacturer website, download the appropriate driver, and boom, you get working Vulkan support. Easy. macOS is more difficult. Apple are very hell-bent on everyone using their proprietary Metal API. And what you need to do then, if you want to use Vulkan on macOS, is to put an emulation layer. I don't like those because they add complexity to your environment. When you have a problem, you never know if it's in your Vulkan code or the translation between Vulkan and Metal, or the Vulkan Metal layer, and debugging that is tricky. So yeah, if you need macOS, you can do Vulkan, but it's not the best choice. The best choice, in my opinion, would be web GPU. So you may think from the name that's something for web people. Actually, it's more general than that. You can use it locally on your desktop with something like a WGPU in Rust. The goal of web GPU with respect to OpenGL and Vulkan is to improve usability and support of Windows, macOS, and the web, obviously, so that you can write code that runs pretty much everywhere, including on old hardware where you were previously forced to use OpenGL. There is a price to pay for this, however. This is a young API, which means that it still changes quite often. So you must be prepared to update your code regularly as the API evolves. And the hardware, advanced hardware feature coverage is worse than in Vulkan and OpenGL, where it's top-notch. And because it's an abstraction under the hood over OpenGL, Vulkan, Direct 3D12, Metal, WebGL, and so on, this means that you will have a harder time with tooling like debuggers and profilers, because these tools will show you what the abstraction does under the hood and not what your code did. And you need to be able to mentally translate between the two. For this reason, if you are only targeting Linux today, as most people in HPC do, I recommend sticking with Vulkan for now. But keep an eye on WebGPU because they have a huge amount of momentum and I expect it to improve immensely over the year. Still, Here, I talked about the first 90%. And since you started seeing this slide, you've probably been asking, what are the remaining 10%? And the remaining 10% is the ease of writing code. That's the biggest issue when you use something like Vulkan to write compute code. These APIs are much lower level than what you are used to in CUDA, Sycl, and so on. If I take the worst case example of Vulkan, which is the most advanced API that allows you to do the craziest thing, before you can do anything, you must first load the Vulkan library, set up some API instance with some global configuration. This is where you say, where error messages from your graphics driver should be logged. Then you need to enumerate the available devices, on a typical computer these days, you can have multiple GPU. You can also have software emulation of the API on CPU, which is very convenient for CI, for example. You need to choose which one you are going to use. You can use multiple ones if you want. It's just going to get here. For each of these physical devices that you have selected, then you will need to set up, using some extra configuration parameters, a device context complemented with one or more command queues, which allow you to submit orders to the device, whereas the device context is allocating resources mostly. Then, once we have this minimum setup, anytime we want to do a particular computation, we'll need to think about a few things. We'll want to write a shader, which is a GPU program, basically, with a specification that tells the compiler how this shader is going to communicate with the host, the CPU side. This will take the form of memory objects like buffer, images, samplers, etc. This shader will then need to be compiled, and this goes in two steps in Vulkan. First, you compile it into some intermediate representation called SPIRV. This can be done when you build your code on your development machine. And then on the user side, this SPIRV intermediate representation will be into binary optimized for their specific hardware and device driver. You will need to set up some memory resources representing storage that you're accessing. So we're going to need buffers, images, maybe samplers if you can see image accesses. Then you are going to need a compute pipeline. This this combines your compiled shader with long-lived parameters that are not going to change, specifying the interface between the shader and the host. Finally, your memory resources are quite unwieldy to manipulate individually, so you are going to want to group them into something called the descriptor set that must be designed to be compatible with the appropriate compute pipeline. And finally, once we have done all that, we're ready to build command buffers, which are batches of commands that we send to the GPU. In these, you will typically pick a compute pipeline, attach some descriptor set representing associated resource, schedule one or more run of the shaders, maybe change descriptor set, schedule some more work, etc. All of this you do before you send any work to the GPU. Then you will build this command buffer, send it to the GPU using a command queue that we made earlier, and you will need to handle synchronization to wait for when the over or schedule other work. So as you can see, quite a bit of complexity. It has some cons. If you are someone who cares a lot of performance, you may find this interesting. You have a lot more control in Vulkan than you have in something like CUDA. You have a lot more headroom to optimize, to get your code faster. The con is, even when you are trying to do easy things, you are forced always to juggle with all these concepts from the start. And this is particularly hard for people who get started, for beginners, which is a problem, because if you want people to use these APIs, we want them to be beginners in the beginning. On the host side, you can make your life much easier by doing two things. First, do not use the APIs directly. Prefer high-level bindings like Vulkan that can automate tricky parts for you. You will almost never need to tune these parts for performance, and they are quite tricky to get right. You will want to extract common work into a reusable skeleton that you can use in many different applications, so that you do not need to change many different pieces of code when you discover something new about your use of Vulkan. On the GPU side code, today we need to make an extra choice, which is which language you are going to use. Previously, we were forced to use a dedicated domain-specific language dictated by the graphics API. This was GLSL for OpenGL. This is WGSL for WebGP. And these domain-specific languages have some pros. They are very easy to learn. They are mature. They are pretty easy to use, and for simple tasks, they work quite well, and they hint you into the way to program a GPU that is most efficient for GPU, instead of pretending that your GPU is a CPU and hoping for the best. On the other hand, the big issue is that because this is a different language, it's very hard to share code. You constantly need to keep type and function definition in sync between your GPU code and the host code. And this is a good area of bugs when you use Gix APIs with these DSLs. This is why there has been a long-standing desire to be able to write the GPU side code in Rust. This is young, but today it's becoming possible. There is a project called Rust GPU, which has been around for a while. These days, it's getting pretty mature, and we can start doing some work with it. It emits Sycl for Vulkan consumption, and it has a high-level CUDA-like layer called kernel that I have not gotten the chance to try yet, but it looks very interesting, and I hope I get the chance to show it to you during the school so that you can see what's next. A totally different approach that has different trade-offs is kubectl. This one is made by deep learning people who want to do fancy tensor operations at GOT. And so it, in order to achieve better optimization and to be able to reuse existing work with other API, kubectl is focused on not using Vulkan directly, but using backends individually, so that, you know, if you use CUDA, you can get in touch with NVIDIA about your CUDA problems. Pretend you are doing CUDA, they will be fine with it. I'm not sure I like this, but in any case, web GPU backends will make your life easier on macOS, so that's a pro. And finally, the youngest option that you cannot actually easily use today is LLVM offloading. There is ongoing research work. The aim is to be able to use the OpenMP for offload backend of LLVM in Rust, so that then, you know, we can benefit from the work that's done to allow C and Fortran code to send work to the GPU via OpenMP in LLVM. As of today, if you need to run an application in a production, I would advise sticking with the domain-specific languages, as they remain a lot more mature. On the other hand, kernel and kubectl are very interesting projects that I expect to grow in the next years. I will, if I can at all, present them at the school and give you an introduction to them, and I advise you to keep on them. Now, all these Grasland APIs I mentioned have a big pro, which is that you can do real-time visualization with. And since we can do that, it would be a shame not to do so. So here's what we get. So this is basically a live computation of the Gray-Scott reaction diffusion system that we are going to study at the school. And unlike most of what you've been seeing in other courses, we are not pre-computing results ahead of time, then turning them into bitmaps in an operation that takes ages. We are doing everything in real time, and almost everything on the GPU. What you are seeing here is my GPU on my desktop computing the reaction in real time, displaying frame screen as soon as it finishes one step. It's amazing. No one else did it because it's too complicated with other frameworks. Enjoy it. There are a few other things that this implementation achieved that I have not seen elsewhere. First of all, because Vulkan, unlike other technologies, is actually portable, it I can iterate on non-NVIDIA GPUs. I could do all the development work on AMD GPUs without any issues. And yet, when I first ran the code on an NVIDIA GPU for a test before the last edition of the school, it worked right away, no change needed. If you've ever played with OpenCL, Sycl, this is amazing. No other GPU portable framework achieves this level of seamless portability between a GPU manufacturer. This is groundbreaking. And yet, at the time, this had the best measured performance. Still, since then, Pierre has managed to beat it in some configuration. You do not lose performance by using Vulkan. That's something very important to remember. How about distributed computing? Here too, Rust has options. They are just not as mature as what we have in our environments. For classic SPC work, we do have MPI as usual. The bindings are pretty decent, a bit rough on the edge. And we have early prototypes of partial global address space like Lamella. What is more interesting to me is that the ongoing R&D I see is not focused on HPCs at the moment. It's more focused on big data use cases, which drain more developers. We get things like, you know, data frames like Panda, Python, based on Apache Row using the Ballista framework, which under the hood delegates to something lower level called data fusion. We get RYO, also based on data fusion, which tries to see how far we can push the performance of streaming SQL, because SQL is what many people are used to in terms of query language. On the other side, we get things like Renoir and Timely Data Flow, which try to do what Ryan did, but for distributed computing, having distributed iterator streams and using them. And overall, this means we need to choose today between several strategies when we do distributed applications in Rust. Should we stick with good old raw MPI? It's a bit boring. It works today. It's simple. Should we invest time to improve some of the higher level HPC framework? Or should we adapt some of this nice big data tooling with lots of developers to our needs of scientific computing? I think this is one of these questions does not have one right answer. The best choice depends on your project. For example, how well it matches these programming models. I want to quickly go over another matter because it's never covered in another presentation. I think that's a shame, which is that most real-world numerical computing code does not only involve number crunching. We are going to need configuration, this network IO, plotting, documentation, test, benchmark, binary packaging. You know, it feels in many ways that most of our computing courses are like you draw an old mem. You know, how do you draw an old? Well, first you draw some circles, that's easy, and then you draw the rest of the whole, that's easy as well. Don't bother me with it. Okay, we are done. Yeah, that's not how I work. Okay, I know that these can be a fair bit of work in C++ and Fortran and so on, and they are quite a pain, and I want to show how much easier it is in Rust. Let's start with configuration. So most of you will be doing command line utilities. We have a great library for this, which is called clap. The way clap works is you define data structure, annotate it if needed, and then clap will automatically derive an argument parser that documents your arguments using the doc commands of your code, puts this comment at the top level, allows you to have short arguments, -i, or long arguments, -- input path, default values, and then you just need to type arg parse in your code and you're done. This kind of driven clear argument programming is amazing. You get argument parsing, type checking, head text generation, all for free. It's a lot more convenient than even what we have in Python, which is already very good. And you just get, in the end, a pre-filled struct with members that are what the parameters your user specified, no extra server-side. If you need to do some structured I/O like CSV, JSON, again, Rust has you covered. Using code generation with macros, you can get, you can just define your data model with annotated structs. And at the end, you take bytes of JSON, send it to a library called JSON, and it will automatically generate this struct with all the parsing, checking, and so on. For more tabular formats like ADF5, we do not need this. We can just use ND array types, and that's what SDA5 does. Now, if you've ever done some I/O, you know that I/O code without error handling is incorrect code. And the reason people do not usually do error handling correctly in C, C++, and so on is because it's hard. Rust makes it easy. For basic operation, you may be happy with just propagating errors to the caller with some extra context information. It feels a bit like exceptions in other languages. The libraries that you want here has anyhow and here, and the result you get is that, you know, I load my data point. If it fails, I have some context that I was trying to load some data from Criterion so that I do not get just JSON parsing error, but I know it's a problem with parsing JSON from the Criterion fork, and so on. In libraries, you do not want to do this. You want to have specific errors that allow clients to take action on error. Like, for example, you may want to recover from some error on the application side. If the network request failed, you may want to retry it after some time elapsed. If the user puts in some incorrect input, you may want to ask them to correct them and try again. You may want also to adapt error message to the audience, translate them, hide sensitive data, and so on. This can be done with this error, which again, with struct annotation to easily define this kind of composite error type where you clearly specify the error cases. Need some plots. We have Plotly, which is a lot more convenient than the horrible user experience and performance of matplotlib in Python. And for static image, we have many options. Plotters is the easiest to get started and most mature. We also have notebooks because these days it's a must. And one thing you may have noticed so far is that I have mentioned lots of libraries. Rust on the scale from C people who wrote their own hash map to JavaScript people who will import a library to pad strings, Rust is closer to JavaScript side, which will make some people nervous. The reason for this is that it's so easy to manage dependencies in Rust. You want Plotly, you do cargo add Plotly, done. The problem is people, when you do this, you must not forget that dependencies come with responsibilities. When you have dependencies, you need to keep them up to date. You need to handle update breakages. You need to have a strategy if the maintenance stops. You need to bear in mind supply chain attacks if your software is security critical. It's a trade-off, right? It's not a pure benefit. Be aware of it. Rust comes bundled with excellent documentation tooling, much better than what we get with Doxygen in C++ and Fortran. It's trivial to set up. Just run cargo doc and your documentation is generated. When you push a library, the doc gets automatically uploaded, generated and uploaded on the web. The language support, unlike Doxygen, is flawless because it's integrated to the compiler. It's much closer to the Markdown syntax that everyone is used to these days, and the examples in your documentation are tested automatically when you run your tests. And thanks to all of this, you can get great documentation and, shows you a real introduction to the library because people do not need to spend all this time in minutia and can just spend more time writing the important part of the documentation, which is tutorials, high-level overview, sort of stuff. Testing is also very easy. You just write some annotated code. It works. Benchmarking, a bit more boilerplate for annoying reason, but in the end, you can just add more statement to this function as you add more benchmarks, so it's not the end of the world. And it will give you nice HTML performance reports with lots of precise statistics, which are supplemented by high-quality console outputs. This means that never again will you need to time your loops in a single run, forgetting to handle noise and so on. Again, Criterion has you covered. It has robust statistics. It can handle operating system noise for you. It's much better. If you've ever need to distribute binaries to user, you know that, especially on Linux, it can be a headache. Cargo Disk makes this easier. Just add a job to your CI and you get automatic GitHub releases with installers, package. Nice. Overall, I like to conclude by saying that many numerical computing projects these days need to constantly juggle between two programming languages. One that is easy to get into, like Python, but turns out to have poor runtime performance and also to have a design that scales poorly to large code base. Like Python's lack of static typing in this respect is a real hindrance as soon as your project grows beyond 10,000 lines of code. On the other side, you also often have a second language that requires more investment, learning investment for programmers. But once you get to know it, you will find that it has scalable performance and features that work better for larger projects. So people combine them as a NumPy, for example, which is a weird hybrid of Python and C and Fortran. But this has many drawbacks. Frequently, you will find that a specific part of your Python code is not fast enough and needs to be written in a different language. You may lose some time to NumPy and Python before discovering that these are really special case tools that generally do not work for most purposes. So then you will need to rewrite in C lots of Python code and write the interface to it. You will get a problem that it's not the same people that know Python and C, so you get isolated subcommunities in your project that struggle to work together. And each interface you have between C and Python, for example, will be an area where you can have performance and lots of code complexity. And you will need to work around it, and it will be painful. These people, try to express simple things using very complex NumPy operation just because they want to cross the interface between C and NumPy as few times as possible. Because of this, we would all love to have a single language that's usable everywhere in the big numerical computing project. Some languages like Julia and Mojo try to get there by improving Python's performance and type system. The problem is that these languages, to be familiar to Python program, do not take the important step of enforcing a stronger type system, encouraging people to use cleaner coding practice, proper software engineering practice. And this again will bite later projects down the road. This is why I'm wondering personally if Rust could go the other way and become the C++ of sane people, suitable for both low-level and high-level programming. This may sound crazy, yet as we see in the community many developers are former Python and JavaScript developers that came and just stuck around. So maybe it can happen. I don't know. The way I want to conclude is, as you can see, the Rust language and library still has some rough edges, but it can take you very far already in numerical computing projects. The main thing we did now is not anymore language features. It's mainly motivated library contributors who are ready to fill some remaining gaps in the library ecosystem and round out some bugs and so on, and support some some use cases like distributed computing. And my question to you is, will you stop hurting yourself with C++ and Python to join this great Garthnization effort? I'm ready for your question.
Okay, thank you, Hadrien. So there is no question for now in the chat and in the Q&A section, but I have a few of them, so we'll try to make it quickly just to not be too late. Yeah, just a little remark. We did not implement, again, I say that again, we did not implement the real-time visualizer for the other language because it's not the goal of the school, because as many of you, you will have a lot of time for the simulation and you have a costly simulation and you have no way to visualize it in real time. So it's totally normal to not do that. Maybe next time we will do it because it's fun also.
Again, the reason I did it is because if you use Vulkan, it takes 1 week to do it. It's a trivial project. Well, not something you want to do during the school, but
1 week is not trivial.
No, but I mean, compared to the time it took to optimize everything else, it's a drop in the bucket.
No, for me,
it takes months to prepare such a school.
Yeah, but not to implement. It takes months because we implement a lot of ways differently, a lot of technologies, but technology by technology is few days, few hours to get the test. So, but yeah, that's not for just for this part. So I will try to get some question. Yeah, for the beginning, just to clarify a bit. When you are speaking about read-write alloc, when you are borrowing some elements, is it about one element or about the full vector? Just to clarify it.
When you type an ampersand in Rust to borrow some kind of expression, at present time, if you do it with an array and index a specific element, it will borrow the entire array. This is a known ergonomics pain point. Basically, the way you fix it in everyday code is first by doing less explicit array indexing. Most of the time, with correct use of iterator, don't need to. And second, by using some methods on the slice type, which is the view of all arrays, which allow you to get borrows of multiple elements at the same time with slightly more convoluted syntax.
Okay, so you have to be careful once you use that to be sure that you don't have problem. Okay. Oh yeah, a question about the vectors. Can you change the allocator of the vector as we can do in the std vector in C++, or can you change a trait, for example?
What you can do easily today is to change the global allocator used by your application. Like you can switch from the libc, dlmalloc to alloc, memalloc, that sort of stuff. Okay. If you need a more fine-grained allocation strategy, it's a bit more convoluted. The most popular model today is to use arena allocators, as in video games. The idea is that you prepare a big block of memory upfront, you slice sub-allocations in it that you never liberate, and then you drop all allocations at the end to avoid the constructor overhead and the overhead of a general purpose memory allocator. You get this sort of specialized memory allocator, but generally, yeah, customized allocator are an area that's relatively young in Rust, as in most C++ programs.
Okay, so I assume if you can change the allocator, you also can have a padding if you need one, or you can tweak that. Okay, so it's nice. So we have a question from Claude in the Q&A section. So you did not mix CMD and multi-threading programming. Any pointers, choke points, weird intersections?
So, actually, I did. The reason I did not show it, on the other hand, this is a presentation. This by nature have to be relatively short and fit on a single screen, and therefore I cannot afford the full code example that does all the things. So what I did instead is to show you how each step works individually using the naive code in the middle for higher level steps. And then the idea is that by combining all of this, you get a good performance. But no, there are no particular issues here. It's just, in my opinion, the easiest way to mix SIMD and multi-threaded programming is to use what I did earlier in the presentation and set up your multi-threading so that you have some serial granularity, wait chunks of data in the inner loop, and then you process these chunks of data sequentially using your favorite SIMD programming model and instruction level parallelism scheme.
Okay. And yeah, you talk about Rayon and with the into par iterator, so you can parallelize your iterator. Is it possible to dream about into unsec iterator or into unordered iterator to be able to have the interleaving that you mentioned really briefly to optimize the reductions?
So, in my opinion, which may be contentious, unsec in C++ is a mistake. It's basically pragma and PSCMD all over again. We keep thinking after all these decades that by just telling compilers that something is SIMD, they will magically become more clever and manage to automatically do SIMD correctly. It's like, CPU, GPU portability, one of these things I think we've been trying for too many years, and it's time to admit that it doesn't work, and explicit programming is the way.
Yeah, in fact, in that case, it depends on the backend and the compiler, but okay. Question from Jean. Is it easy to use my own Rust library from C++ or C? And the other way around, can Rust easily use C++ library like big linear algebra code?
So this, I will add some nuance because you are mixing C and C++ here, and the answer is not the same for the two languages. Rust has very good interoperability with C, which is the de facto standard for interaction between programming languages. You can define Rust functions that are callable from C, and you can call C function from Rust quite easily. There are even very convenient tools that automatically generate the glue code for you, things like bindgen and cbindgen. C++ is trickier, it's a bit less advanced, and the reason why it's more complicated is that in C++ you have templates. And the way templates work is that you need to have a C++ compiler around in order to generate template instantiations. This creates a challenge for things like Rust because we do not really want to have a plugin to the Rust compiler that calls into a C++ compiler every time instantiate a template if we can avoid it. Still, there are some solutions here, less mature. I think CXX and AutoCXX are the most advanced options here. So what they do is they provide easy interoperability for common types like std string and std vector, and they allow you to specify more complex interfaces in an interface definition language that will then transpile to Rust code and C++ code. This works, but it's still pretty limited. I would strongly advise C++ projects to consider exposing C APIs, because one thing C++ programmers always forget is that the only programming language that can easily interact with C++ is C++ itself. If you want your code to be usable from Python, from Julia, and so on, from Java even, you really need to have C APIs. I know it's a pain, it's a bit boring, do it, and it will make multilingual workflows much easier later on.
Okay. And yes, speaking about ND arrays, are they aligned? Can you use padding? If it's a normal API, I assume yes, but can you confirm that?
They are as aligned as the element type. So
okay.
The classical trick when you want alignment in Rust is to basically use a SIMD type inside of your array.
It's an RF wide as we can have in EV.
Exactly.
Okay.
It's also what I would recommend C++ actually, because it saves you from all the work of the built-in assume-aligned crap that you need to have when you have arrays of scalars. So I'm not terribly unhappy about this.
And yeah, I join you also on the fact that you don't want to rewrite your matrix product yourself, because even on big matrices, you have a way to break down the complexity of matrix product, and so do not reinvent the wheel and use the.
I felt it was important to stress this point.
Yeah, it's really important. Yeah, you don't want to do that. In fact, for small matrices also as well, you don't want to reinvent the wheel. Yeah, speaking of OpenGL, you said that they are used global variable everywhere. Generally speaking, if you pronounce the word global variable, you will have some problem at some point. So as Sebastian explained to you, as soon as you get some unit testing, you don't want to have global variable in your program, just to be safe.
It's a for testing. It's a pain for NUMA as well. It's a pain for multi-threading.
It's a pain for everything, so don't use them.
I mean, they are fine some specific stuff like, it's okay for the system clock to be a global variable. It's okay for the logger to be a global variable. For anything else, for any data, don't.
Yeah. In fact, I assume that if you joined the webinar today, you are a bit curious about Rust. So don't be afraid by the complexity of Rust. It's a language to learn. It's an investment. You cannot learn it in few hours. It's not possible. But it's really interesting in terms of design, because you are forced to think differently compared to what you are used with Python, with C++, with C, or with Fortran even. You have to do this investment just in fact we did that for fun in the group, because it was fun to rewrite some stuff in Rust, just to have another point of view of what we did in C++, and in fact it's really nice.
Yeah. I personally find that it often it often hints you into writing things in a way that works better. Yeah. Like, for example, this focus on immutability will make your life much easier later when you do parallelization, because then you have less synchronization between your threads, and you can better leverage your CPU caches and so on. It's different, but I think it's different. Usually different in a better way.
Yeah, it's different, but it's logical. In fact, yes, some stuff are a bit weird in Rust, but you will struggle with borrowing. You will struggle with this kind of stuff, and with the error message also at the first part, because they are not as usual as we can expect in C++ or in C. But with some practice, just try with small projects at the beginning. Of course, if you try a big project, you will have a problem. But small projects, step after step, and just to feel what you want to do in Rust, to integrate also the traits concept, all the function, all the way you want to implement stuff. And normally you should get with you should have something nice also at some point. Not few hours later, of course, but you have to play with that, all this concept, and normally should be quite easy. As Sebastian said, you are not obliged to use Rust in production, but you can say, okay, let's rewrite these little pieces of our software in Rust and just see what's the point.
I would also encourage learning it, even if you do not necessarily intend to make heavy use of it in the next few months, just because it gives you a different point of view. It's like, functional programming languages as well. I strongly encourage people to learn one of those. They give you a different point of view that you will find very useful in some kind of work, like compilation, for example.
Yeah, and also, since you're starting from an existing program, so you know what to test, you know what is the design roughly, and you can go really faster on the implementation of the Rust version. And then you can play and say, okay, let's add this functionality, or let's tweak that to be maybe more user-friendly. And you can play with that, and then you can improve your C++ implementation because of your little test with Rust. So it's quite interesting to give it a chance. But you need to have time for that, because it's not magic. You will struggle a lot to get used to all the concepts.
Yeah, both Rust and C++, I would expect a few weeks before you are comfortable doing simple projects, a few months before you are fully efficient.
Yeah, even you still have to learn a lot of stuff. A few months it's for really simple projects, but yeah.
I would say a few months is to get the 80% of efficiency, where you are still avoiding some stuff. That's okay. You will learn it later on.
Yeah. You have mentioned also macros and proc macros and stuff like that, but it's really advanced stuff, so you can limit.
I showed them
you can limit yourself to really.
And line interface. this is all possible due to macro. They are effectively the introspection of C++ of Rust.
Yeah, but it's still quite difficult to use this proc macro because you have to understand how the compiler works and how the intermediate representation works. So it's not for beginners. So use it only if you had to, or if you want to do for fun. In fact, we did that for fun also with the team. But yeah, you prepare yourself to struggle a bit. It's normal. It's a learning process. But at the end of the day, I think it's worth it. So. And you will discover also all the bad faith of Hadrien about Rust and about C++ with that, but I don't want to.
I try to be fair about drawbacks.
Yeah. And then, yeah, about Vulkan, you will have a lot of, you will see all the low level details of all the GPU. But at the end of the day, you need, I needed 3 hours to create a triangle, but I was really proud of my triangle. So, and you understand all the weird details behind, under the hood, and hidden with, as you mentioned, hidden with CUDA, hidden with Sycl, hidden with all these high-level APIs, because they are high-level APIs, in fact.
Something also that's not said enough, I think, about Vulkan is, okay, it takes you 3 hours to draw your first triangle, but yeah, it will not take the same amount of time to draw the second triangle.
Yeah,
there's a lot
in fact,
amortized,
it's really smooth. Here. It's really efficient. You know that it's really fast under the hood. You know that there is only your triangle and not a whole bunch of stuff done around it, and it's really pleasant. And you can have a look. You can start Vulkan with a bunch of example, because in Chronos Group they have you have, I don't know, maybe 30 examples with a lot of stuff, and they are really good. So you can start from that. I didn't start from it, in fact. I start from scratch and I say, okay, let's figure out how to draw a triangle. I think it's not a good idea. Maybe start with real example from the Chronos Group, and then we can dive step by step, rather than to get, okay, I need to write 1,000 lines of code to write a triangle, and I don't know where to begin. Just maybe the opposite way is better.
Thank you all for joining, and I hope you learned something interesting today. See you at the school.
Okay, so let's wrap it up. So thank you for joining us today. So next week we will not have a webinar because it's another day out in France, because it's May, and in May we have a lot of day out in France. So the next time will be the 5th of June. So we'll talk about Python on GPU. So computing with Python on GPU with a lot of libraries. So don't miss this one also. So no webinar next week, but the week after. And have a good day, and see you the next time. Bye.